So this lambda by 2 of I told you that this W transpose W, you can simulate it with the term like x square W square. So when you differentiate it with W square from W, so when you differentiate it with respect to W, you will get 2W. So similarly, when you differentiate W transpose W, you will get 2W. So this you will get 2W here, and this 2 get cancelled with this 2, right? So how this lambda W comes away? Now there is no 2 here. This there is 2W, there is 2 here, there is 2 here, right? But this, if you observe, there is a half here also. So when there is this will generate 2, and this 2 is also here. So this 2 cancel this 2 and this 2. So that's how all these 2's goes away, right? So I hope that this makes sense to you now. So the some other question is, when to use least square and gradient descent? Okay, that's a very nice, good question. So the least square, the least square is known as when you have a closed form solution. Closed form solutions means if you remember, if you know that what is gradient descent. So gradient descent is when you don't have exactly, you cannot find out what is the maximum or minimum. For if you recall that maximum minimum problem, what you do it, you you take a gradient, and sorry, you differentiate it, and after differentiation you put that it equals to 0. Whatever the value you get from that expression, that is either minimum or maximum, right? So you here you can observe that you directly getting the min or max of the function by help of this differentiation. But if it is not, if you don't find this directly, for example, because here you, if you observe carefully, you are just doing some algebra, and in this algebra you are getting you are getting directly the solution of min and max. But in some cases are there when you don't get a closed form solution. In that case, you don't know where you are. But if you are sure that your function is exactly the convex function or convex function, for example, this is a convex function and you are standing here, so you know if you use gradient descent, you always walk towards the minimum, the local minimum, local minimum point, step by step. And if you are just crossing it, you will see that your whatever the value you are get, you got so far here, this is increasing now. So from this step, as you take further step, you will get to know in gradient descent that you shouldn't move further, because this is the minimum value you got in this range here. And in gradient descent, you never get exact value of W, right? But in this closed form solution, you always get the exact value of W. Why you don't get exact value of W? You will always get a range, that in this range this is minimum. But when you have a closed form solution like these gradient things, whatever you are getting here, you will get exact value of W where it is minimum. So in short, where the closed form solution is possible, you get this solution, this kind of solution. And if you don't have a closed form solution, the function is very unknown, and you know, just to find out the local minimum of it. For example, this is a function and you are here, right? So you can get this up to, by gradient descent, you can get this point at maximum. If you are standing here, you can get this point here. So in gradient descent, every time, if it depends upon from where you start, your minimum will get changed if there are so many minimums. But in closed form solution, there is a unique W is there, for example global W, and that you will get it. So I hope that you, once you get a lot into these details, you will get more clear understanding where to use what, right? So I hope this makes sense to you now. So there is one question, sir. How function has been expanded after taking 3-dimension input? Oh my God. So I haven't thought it about it, but if you if you see, you can if you want, you can come up with a solution. Let me think about it. I haven't think about it. Right. This was actually, I introduced all these expansion just to make you understand this, how these things look like. so that it will not be very abstract to you, and you what is the phi function, right? Generally we don't go, we use Gaussian basis functions and all, but the motive of this lecture is not to go into that detail, but how to use the basis function in linear regression. So we will see. I will try to, for you, I will try to come up with that solution. If I will try to post it, right? So okay, this slide is from the previous lecture, introduction linear model for regression, right? So what is this? I don't know. Okay. So this is can we there? I just want to recall you that what is the likelihood of a data set? Likelihood of a data set is, for an example, this is x1 t1, x2 t2, up to xn tn. So these are different and different samples in a data set, and you want to find out what is the likelihood of this data set. So you take the probability of this sample, you take the probability of this sample, if you take the probability of this sample, and if they are independently drawn from a space, then you can multiply all these probability. This is called the likelihood function. So I don't have to repeat it, because I know I have covered these things into two detailed lectures. What is likelihood function? So this slide is to recall you, if this is a Gaussian likelihood function and x is a Gaussianly distributed. So for an example, this is a Gaussian distribution and you get some x here, and you know that there is a mean. What is the likelihood? You take the probability by the, what is the probability you get x1, what is the probability you get x2, what is the probability you get x3, and this is the Gaussian distribution formula. So this is the probability what you get by x1, what is the probability you get x2, what is the probability you get x3. Now you are getting all these expression again and again by x4, x1, x2, x3. When you multiply all these expressions, what you will get, this constant term will get out. Right, this is a constant term, it gets away, and all things will get multiplied. So exponential a, exponential b, exponential c, they are in multiplication, because the base is same, everything get added. So it will be e a plus b plus c, right? So finally what you will get, e exponential summation, this constant will again get out, and this is x minus mu whole square, right? So in this exponent term, all these things get added, and it will come to into this shape, half into summation. How many terms are there? If there are n different samples, so this will go from I equal 1 to n. So there, because there are n different samples, and for each sample there is a probability, you are multiplying n different samples. So it all things are get added, and different things get added into this exponent. I hope this get understood. So right now I am not considering this. This is the only thing that what I wanted. Okay, great. So this is just to recall. Please excuse me for changing the notation from previous slide to this slide. I didn't notice, but at the last time when when I was about to come to this class, I found that I have changed some slide notation. So please excuse me and sorry for that. But the notation change is that, rather than using as in the previous slide we have used x1 t1, x2 t2, now I have changed this notation from x1 to y1, x2 to y2. This doesn't make any change, but yeah, obviously notation gets changed. Now every time you have seen x, as every time you have seen t, rather than you will be seeing y now. So otherwise there will be no difference. So the data model that you are using in Bayesian linear regression. So what is Bayesian linear regression? We are going into the detail of Bayesian linear regression. So for example, you have these samples x1, y1, x2, y2, xn, yn. So let's say x1 is the customer comes to a market and he is spending this much money. X2 is again the second customer, he's spending this much money. Xn is again third nth customer, he's spending this much money. Your motivation is to find out for the new customer how much money he can spend. So what is the general pattern? Can you come up with that? So this is known in terms of machine learning. It is known as learning the true function. That is for a given new value of X, what is a new value of what is the value Y that could happen against that X. So here xi is a d-dimensional vector and y is a real number. For an example, this is a customer xi. It could have d different attributes like say name, age, salary, family, and a lot of things. So it could have like 100 of attributes. So it goes anyway. And for example, I'm saying how much money he spent in coming mall, so it is just a real number. He could have spent 1,000 rupees, 2,000 rupees, and 10,000 rupees. So why is just a real number? So model is while I know that what is the, if let's assume that given the parameter, the that y1 y2 yn independent given w, so we are assuming that once we know that what is the that y1 and yn are independent given these parameters. So this is the assumption is we have discussed these things in lecture 4. So just to recall for you so that you shouldn't get confused, for an example, this was my hypothesis. Let's say this was my hypothesis, and this is the true points, the true value of y, let's say in this case y. So this is the hypothesis. For this value of x, I am generating this value from hypothesis, and this is what is present in my data set. So this is a sum difference. So this is a difference, right? So we assumed that this hypothesis and the noise is Gaussianly distributed. So the mean of this noise is, if the noise was drawn from a Gaussian distribution, that is having mean 0 and variance this. But if you have a function fx that is wtx plus this let's say this is a noise and it is Gaussianly distributed. Gaussianly distributed means 0 mean and variance. Once you add this value, it gets shifted to this. So the new mean will be this. So your mean now is this, and the variance is same as it is. This variance is square, right? Now, given the value of w, you are multiplying all these things we discussed in chapter in that lecture, Introduction to Linear Interaction. So ultimately, what I am saying, the maximum likelihood will be the product of these things. The only difference is that your the mu is not fixed here. The mu goes according to the hypothesis. So this mu will get changed, and this will be my W transpose X, right? So this mu is the only change from this slide. Otherwise, everything get multiplied, and this mu is the value of hypothesis. When you do all these things, and we also assume that my beta and alpha are known. What is beta? Beta is a precision. For an example, if I am saying that this is my mean, 0 is my mean, and this is my variance. So the precision is the inversely proportional to the variance. So if this is beta and I am saying this is a precision, so my variance is sigma square. So it is just to simplify the notation. Don't think too much about it, and for the time being, think that beta is a representative of a variance. That's it. No need to go into that detail why it is so for a time being, but just to have the point in your mind that it is also ease the computability and analytics. So that's why rather than writing 1 upon sigma square, we write beta. Okay, so this is a this W is these Y are independent given W, and all these Y are Gaussianly distributed where the mean is given by the hypothesis. So just again, I will for you, I again try to explain what does this mean. This, let's say this is the hypothesis, and this hypothesis is given by WT X, right? Every time you have some, you want to predict some value of this X, you come to this mean and find out what is the how much the noise is Gaussianly distributed by the variance. If you want to predict this point, this is the mean, how much Gaussianly distributed it is by the variance, by variance square. So this is these are all independently distributed. So in that case, you need to multiply all these. So you need to multiply all these for in that case your exponent exp, your mean will be x trans w transpose x, right? W transpose x minus your true value, that is y, right? And that is a square of, this is the form of a mean, right? So this is the form of exponent. You can see that this is a form of a exponential. It is given value of x minus mean and the whole square. When you multiply it, you will get this value. Okay, just to discuss little more on it, what it is. Okay, fine. So what I'm saying that we are multiplying because they are independent, because and an independent assumption given W, we are multiplying the things. So what we are multiplying the things, we are multiplying this all these expressions for every value of x, and x here is for every value of x, and mu always gets changed. And the what is the value of mu here is W transpose x or x transpose W. It is say one or the same thing, because this is a d-dimensional vector. Both are d-dimensional vectors. Either you can do to say whatever you do, you get the same result. So this is what your mu will be, W transpose x or x transpose W. This is the same thing, minus x. When you are multiplying all these things, so this will get added into the exponent term from I equals to 1 to the number of samples you have. For example, you have n samples, so you get this expression into the form, into this form I equals to 1 to n, and only this mu will get changed. So this is WTX, right? So for example, this is x1, this is xi, and this is also xi. That's the only difference. When you multiply all these things, so what you will get this this thing into this form, vector notation. Y vector notation, because if you write it is a y vector. Y vector is nothing but it's a y vector is y1 y2 up to yn. So this is a y vector. So y vector minus qw, what does this mean? It means if I want to expand it, so this y is equal to y1 y2 y3 up to yn, right? And this is minus 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 and minus. What is qw? So q is a matrix, if you remember, right? So q is a matrix. So what kind of matrix it is? So here, for example, if I am using my basis function, so this is phi1 x, phi2 x. So this is my first sample. Let's say how I'm representing my samples here. Okay, so this is my first sample. So phi n, phi, how many dimensions I am having? Let's say I am having m dimensions. So this is x1 again, right? This is the same thing I explained previously, and this is w vector. W1 to Wm. So when I multiply this thing with this thing, I get this hypothesis. I get this sigma equals to, or not sigma, this X transpose W, right? Similarly, I get this one, phi X2 transpose W. So likewise, I get phi Xn transpose W. So this is sum of first sample, this is a difference of first sample, this is a difference of second sample. Likewise, I am transposing it and multiplying it, I am getting this expression. So it is nothing but the sum of squares, I equals to 1. So this is nothing but this thing, summation I equals to 1 to n and x minus this wx, right? So this is the same thing. What is alpha? Where I have written alpha? This alpha? Okay, sorry. So this is a proportionality sign. So this is a proportionality sign. So this is, I'm saying this probability of D given W is proportional to this likelihood function. So this is proportionality. And this alpha, okay, let's talk about this alpha. So, sorry for again these two similar kind of structures. So this is a proportionality sign, and this is alpha here. What this alpha means here? So R, D, and R. Where are you, Amir? I just explained it. What is R, D, and R? It's a dimension. It's a space. It's, for an example, I have to say 3-dimension space. I can write it's like the R3. And if I am saying that I am in the single dimensional space, I can write this is only a real number. So n dimensional space means Rn, right? So I am saying my input vector x is d dimension. So it means that x belongs to a d dimensional space. And if I am saying that x belongs to d dimensional space, it means x have d different components, x1, x2, x3 up to xd. And if I am saying y belongs to R, it means that y is a real number. It is having only one component. Okay, so what I was saying, so what I am saying here, so just a quick question from somebody. He is asking what is alpha. If he means to say this alpha that I have written into W. So if he mean by this alpha, so I want to just have a quick point on this. So what we are saying that here, because this is a Bayesian regression, if you remember what is Bayesian, Bayesian means if you want to predict the probability of A given B is equals to probability of B given A into A probability of A, right, divided by probability of V. If I don't write probability of V, rather than if I don't write I, this equal will get converted into proportional. That's the only difference here. If I don't normalize it, this gets converted into the proportional sign. It means the bigger according to this value gets changed. So it is not equal to but proportional to. So why we have used this alpha here. And other than that, this alpha means because this W is the weight. So in Bayesian probability, we know that we have to take the prior probability, and this is the likelihood probability. So this likelihood probability is that what we are calculating, that given W, what is the probability that we get a data, and get the data that we are multiplying it, and we are getting this vector notation form. This is the likelihood probability, but we need to multiply this likelihood probability with the prior probability. What is the prior probability means? Our belief in what is the happening of this A event. So here this is the likelihood probability of the data given W, and what is the probability of a W? So what is the probability of W? So that probability of W, we assume that the prior is a Gaussian here, And what I mean to say this alpha, that the variance, this is I is identity matrix. So I is identity matrix means diagonal matrix. For example, if W is a m dimensional vector or d dimensional vector, so in that case there will be alpha, 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 and alpha. So this matrix will be D into D, D by D matrix, and all these are zeros here, right? So what does this mean? That where if I plot a Gaussian, if I plot a Gaussian for this W, then what I will have? I will have a very circular mountain, very circular mountain, and that peak of the mountain is on the origin, that is zero. That's what it means to say that the mean is at zero, and it is circular, very circular, because the variance in each direction, variance is not correlated to other variables. So here these are zero, and the diagonal is having the common variance, that is alpha, alpha, alpha. It means it is a circular mountain. If I am talking about in 3D, so it will be a circular mountain and it is having a tip at the origin. That's it. So this is the prior probability of W that we are thinking. So now I want to find out what is the probability of a W given data. So this is prior probability. I believe that this W is drawn from this distribution. This is likelihood I calculated from it. I'm multiplying it and I'm getting the posterior probability. This is PW given data. Okay. Final thing. So this PWD is this because I told you that this is exponent. If I write this exponent for PW, how can I write? I can write 2 upon sigma square something 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 exponent into minus half of variance. Variance, let's say variance, because this is a precision. Alpha is the precision of variance square. So I am rather than writing sigma square, I am writing alpha here. So that's why this alpha comes above on that. And then what we do generally, we are subtracting the value of W from the mean, and mean is zero here, right? So this is mean. So that's why we are having here this W trans. So in multivariate Gaussian, if you remember that what you write, W minus mu and that variance and transpose W minus mu. That's how you write in multivariate Gaussian. Here mu is zero. Here mu is zero. We are replacing this variance from the precision factor. So this alpha minus 1 means this is here, and we are replacing this variance from alpha. So this mu is zero. This mu is zero. So that's why this got converted into W transpose W, right? So that's how we come this thing, exponent alpha W transpose W. So this is nothing but the same. This is the formula. This is the probability in the normal form. Right. So this is my prior probability. I'm multiplying my prior probability with the likelihood. Okay. So I'm multiplying my prior probability, that is this probability, prior probability, with the likelihood probability, and this likelihood probability, this probability, and both are in exponential form. So they both will get added, and when both will get added, it comes inside it. So this exponent will go outside, and both they will come into the sum of it. When you multiply both these numbers, these two numbers, okay, so after getting simplification, so this two get outside. We have taken this common half, and this will get inside. Now we are multiplying all these things, these from here to here. what we are getting y transpose y of this expression. Just for an example, I just introduced this step to make you understand that how this when you multiply y minus q w transpose q minus w q, you get this expression. You get y transpose y minus y transpose q w minus q w transpose y plus w transpose q w, because you can write this y minus q w transpose as y transpose minus q w transpose, and this q w transpose you can write as q w transpose into q transpose, right? So you can write this expression like this. Now when you write this expression like this, so when you open this transpose bracket, so you will get y transpose qw minus w transpose q transpose y. You get this thing. So how exactly they get converted into this? So if you see carefully that all this thing is a scalar number. When you multiply q with w, you get a vector. When you multiply that vector with a transpose, this row will get multiplied by this row, you will get a number. So this is a scalar here. If you take if you take the transpose of a scalar, if you take a transpose of a scalar, it will not get changed. For an example, transpose of a equals to a only, but transpose of vector a0 a1 is that. So that if this is a vector a0 a1, then it will get converted into a0 a1, but for on the scalar it will not get affected. So this number is a scalar here. When you take a transpose of a scalar, y transpose qw transpose, it will not get changed. So but in formula how it will get changed, w transpose q transpose y. Okay, so this is nothing but the same thing. These two expressions are the same. You can see here w transpose q transpose is equal to this. So I just what I can do, I do because these two things are same and now minus sign, so we have to write minus twt. So this is how it comes here. Okay, so when we have this, this is a simplified expression. This comes from here only. When we multiply beta inside, so this beta comes here. Now what we have done, okay, so this is a simple arithmetic. This terms is same. I think this term is again same, and here these two terms get converted into this term. So this w transpose is taken common from left side, and this w is taken common from the right side. If you multiply, for an example, if you multiply these two things again, what you will get, w transpose beta q transpose q, and from right you will get w. The second term will be w transpose alpha I, and from right you will get w. So identity will get away, because everything you multiply by id matrix, identity matrix, that will not get changed. So alpha is a constant here, alpha is a scalar number here, so alpha w transpose w will come back, and from here you can see that beta is a constant. It will, you can take from on the left side of this expression, so you will get beta w transpose qw. So this is how these two terms get converted into one term, and it is w transpose. Inside the bracket we have some number, and on the right we get w. So this is what we are saying, that the posterior probability of PW given D, it's multiplied by likelihood probability into the prior. After doing some multiplication, the posterior probability is proportional to this expression. Why we are doing this? Why we are doing this? When we come up with this expression, see, Now just put a hold here and come to this point. Come on to this point. So what generally we have, if we want to write some Gaussian distribution, we have this form in a multivariate case. Right, in a univariate case, what we have, x minus mu square upon 2 sigma square exponential upon 1 upon 2 pi something sigma square into root. Right, this is a univariate case. But if you write the same density in the multivariate case where x could be more than one dimension, you have to write like this. So here this is a precision factor, that is here correlation, where this is a covariance, this is a covariance matrix. So this matrix is, this L lambda is a covariance matrix, and it is inverse of a covariance matrix. So this is a precision matrix, and it is inversely proportional to the covariance matrix. So this is the same thing. So what I'm saying here, if you want to write some multivariate Gaussian for distribution, you can write it like this, where this is a mean mu and this is a variance matrix, and it is a variance matrix. So this is how you write it, right? So okay, so when we multiply it, we get this thing. So finally what I am trying to say here, that if you have some multivariate Gaussian expression, the form of this multivariate Gaussian expression is this. So every time you see this form, you can say that this is a multivariate normal distribution. So this is a multivariate normal distribution. We have proved it. We started with the density function, and with that density function we come up to this stage, right? And we have seen that this is what we got. Now let's match this thing. Let's match this expression with this expression. We get some constant term here, right? This is a constant. So this is a constant term here. I am getting W transpose. I am getting W transpose W. So I am getting W transpose W. So in between, this is a variance. Oh, this is a precision matrix. So this is a precision matrix for me. When I'm coming here, I am getting this is. So when I'm coming here, this is my weight vector multiplied by precision matrix multiplied by mean. So it means this is equals to this expression. So when I multiply, when I put this expression beta W transpose Q transpose Y equals to this expression W transpose Q, here this W gets cancelled. Now I get lambda mu beta Q transpose Y. This is what we got. Now finally when I got why I want to calculate mu, this is this expression, right? Q transpose Y. So ultimately what I mean to say in the crux, that when we calculate the posterior distribution means that I have a data, right? From that data I calculated likelihood function. Like I got likelihood function, I assume some prior also on W. So this is my prior. When I multiply likelihood into prior, I get the posterior distribution. That posterior distribution is also a Gaussian distribution, right? So this is nothing but a Gaussian distribution, and you know that Gaussian distribution is having a mean, and that mean is having the highest probability. So if I want to do the maximum a posteriori estimation, what is maximum a posteriori estimation is when you multiply by likelihood by prior. How you maximize this expression? How you can maximize this expression? That is in maximum likelihood, you maximize only likelihood expression. But when you use map estimation, you maximize this expression likelihood into prior. So this is the expression This expression is getting maximized because this is a Gaussian distribution. This is a Gaussian distribution. So this is get maximized on the mean of it. So this is the mean. So if somebody comes and asks you what is that maximum posterior estimation, so it is nothing but the mean of the posterior distribution, because mean is having the highest probability, and you can calculate this mean by using this formula. This is again a closed form solution, and the variance is this. So once you will find out that the maximum a posteriori estimation is nothing but the mean, and this mean, to get further simplified, this is a variance, this is a precision, right? And this is the inverse of it. You put this value of lambda here. This is, you see, this is lambda, right? This is lambda matrix. So you put this matrix because this is the inverse. When you want to bring this beta inside this formula, it will get converted into the 1 upon beta. It will get converted into 1 upon beta because this is the inverse here. This beta will get cancelled here, and this will remain. So this Q transpose Q will get here, and alpha upon beta will get here. So this is alpha upon beta, and this is I. And finally I get this expression. Now just want to relate that when I was doing my this thing regularization, I have taken some regularization term. I add this regularization term with error function. I did some algebra on it. I got this expression, right? I got this expression. Just see this expression carefully. Now when I am doing Bayesian estimation, when I'm getting Bayesian distribution, I am getting this W, oh, sorry, this W, and this is that W, which when I'm using regularization, you can see that this W is exactly similar to this W. Here this is the lambda we used for regularization. Remember, lambda by 2 W transpose W. This is the lambda we have used for regularization, and here lambda, it means the regularization term is alpha by beta. Here regularization term is alpha by beta. One last note on it, that this alpha by beta is equal to the lambda in regularization. So what this alpha was? This alpha was the variance of this W prior. If I make this alpha as infinite, it means I don't want to take any prior on it. And if I don't want to take prior on it, then I will have only left with Q transpose Q. Okay, last slide. So I don't expect this slide in examinations, and this is just for the sake of completeness of syllabus and for your understanding. So so far what we have done. Hello. So sorry. So finally you will get this result, and here the mu and the variance are the same. So this is called the prediction finally. So I don't expect this slide from you in the examination, but yeah, for your sake, you can understand, you can take it for the sake of completeness of the syllabus. Right. Thank you. Thank you, sir.